I wish you a great new year, 2023. Today is the first lecture series again in this year, and we start with a very interesting presentation from Dr. Ryyan Khan from Bangladesh. Just a few information before we start, so please mute yourself so that we don't have any distraction during the presentation. For now, we will have around 25 to 30 minutes in presentation, and then afterwards you can ask questions either verbally by raising your hand, or you can just type it in the chat. In total, the lecture will last 1 hour. We have this lecture every Thursday, so you're welcome to use the same link every Thursday to join the lecture. Every week it's about a different aspect of agrivoltaics, but it's all the time about agrivoltaics. And it's sometimes from the science background, sometimes from the politics background, sometimes from the practice background or agricultural background. So it's pretty diverse. And yeah, I can invite you to look at the program, which we have on our website. I can also share the link again for that. You can also download all past presentations from a cloud we have. I will also post that link into the chat. But now I give the floor to Dr. Ryyan Khan, and I wish you a very interesting presentation and discussion.
Okay. Thank you for inviting me to the talk, and thank you for arranging the lecture series. Just a brief background. I'm Mohammad Ryyan Khan, Associate Professor in Electrical and Electronic Engineering, East West University in Bangladesh. So as you can see, I am in Electrical and Electronic Engineering. So yeah, I do mostly electronic engineering part, so the energy part of PV. But I started off with thermodynamics and solid state physics of solar cells, then moved on to panel array system output. Now I'm kind of moving on to more compound systems such as agrivoltaics, floating PV, and so on. So hopefully you'll find it interesting. I'm very confident about our energy calculation part, but hopefully you'll find that the other parts, the crop modeling and the economic modeling are, well, at least okay. So if we tell the story of a PV system, you start off with the cell which has its own physics, its own electronics, its own optics. And then as you connect these cells in a series configuration, you get your panel or a module. Now, these panels are used in like a PV array system, where you get the utility scale farms. You can do tracking and get your energy output to the grid. Now, the utility scale farm can be on large fields, as well as it could be on industry rooftops. It could be building integrated systems. And of course, you can have floating PV or agrivoltaics. Now, beyond the energy part, we also need to look into the lifelong assessment in terms of maintenance, such as cleaning the panels to make sure you don't have dust, and also to make sure the panels are not degrading. So once you combine all these concepts, what it boils down to is its cost, or LCOE. So everything is about money. When the investors invest their money, they want to know what is the profit and how long would it take to get back the money. So everything is at the end driven by economics. So hence the techno-economic analysis of my work. Now, you can find a summary of all these things in our book. So this book is by Professor Alam and me. Professor Alam is from Purdue University in USA. Now, if you think about utility scale farms where you need a large field or large open spaces to place your panels, not all countries have such privilege. So you'll have to go for other systems. For example, industry rooftops, building integrated PVs, floating PVs, or voltaics. Now, today's focus is mostly on agrivoltaics, but for floating PV and agrivoltaics, what is common is that you can combine two demands of humanity. One is energy, the other is food. And of course, all of these are tied with the economics and the jobs. So if we work towards a sustainable future, then we somehow have to optimize the systems so that you have sustainable growth of energy for a country, you have sustainable growth of food, and you have clean water, and you have growth in jobs as well. Now, when we think about agrivoltaics, it's mostly utilization of croplands. We can divide it into two concepts. One is that you can place the panels on croplands. For example, if you have a big field of rice or wheat or corn, you can place panels on top of that. The other option is that you start off with your solar farm and then grow shade-tolerant plants beneath those panels. For today's talk, I'll mainly focus on the first one, where you have large fields of crops. So our starting point is that, let's say we have a lot of cropland, especially for major crops such as rice or corn or wheat. These usually require a lot of sunlight, and when you cultivate these crops, you'll see that the fields are very large. You don't have any shading nearby. So ideally, it's like a good option to place panels. So if you do place panels on top of it, you have shading, and shading, of course, reduce the crop products to some extent. Now, the amount of shade and the reduction in crop production, these are not proportional. Typically, this is a linear relationship. So if you do shade by, let's say, 30%, your crop production will not reduce 30%, maybe by 10%. Now, because you're losing out on crop from this land, another option to do FPV would be to give up a part of the land. So you know how much crop production you are losing. Let's say you give up that amount of land and just place panels on top of those. So once you do that, the amount of crop production in those in both A and B, the imposed APV system or system and the juxtaposed system, the amount of crop production are the same, the assumption. But what happens to the energy production? Would you get more energy from system A, or would you get more energy from system B? So our performance metric here is the ratio of the energies. Once you do all the simulations or all the predictions for energy and all the predictions for crop, what you find is that if you allow, for example, 50% loss in crops, then you would get energy ratio over 2. So energy ratio greater than 1 means that system A is better. And as you can see, that in all cases, energy ratio would be in fact greater than 1. But how is system A? Typically, you won't want to lose crops any more than 5-10%. So if we look at the 10% mark, you see that the energy ratio is above 4. So system A will give you about 4 times more energy compared to system B, even though the crop production is exactly the same. So we'll not think about system B anymore, although this could have been an option. It seems like system A would be the better option. We'll focus on bifacial panels for rest of my talk, but the question here is that we understand that the amount of energy would be more compared to B, but is this economically viable? Would people want to invest here? So I'll go through my talk, explain how we can predict such systems, and then what I'll do is that I'll try to summarize some of our results. So here's the outline. I'll start with the techno-economic modeling. So these are numerical models. In an agro-PV system, of course, you need to model the sunlight, you need to model the output of the panel arrays, you need to model the output of the or the production of the crops. So you need a model for panel arrays, then model for crops, and of course, to summarize the profit and the revenue, you need the economic model as well. So in our panel array model, this is quite a versatile model. It could be facing any direction, right? The array direction, it could be south. If you're in the southern hemisphere, it could be facing north. In some cases, you want it facing east or west. Now, of course, the system would be defined by the panel tilt, the spacing, and the panel sizes. And then when you want to start modeling, you need to figure out what is the sunlight, the direct sunlight, the scattered sunlight from the sky, and then also the light reflected from the ground. So just a reminder, we are focusing on bifacial modules or panels. So the analysis is slightly more complicated because now you're collecting light from both the front and the back faces. And of course, the panel output is strongly dependent on the ambient temperature as well. So our PV model can predict output for fixed tilt bifacial. These are the conventional systems. It can do bifacial tracking. We can do floating PV. We can also, of course, now do agrivoltaics as well. Now, this system, our modeling system, works for any orientation. It will work for any day of the year or any hour of the day. And we can predict output for anywhere on Earth. Now, given this system, our second part of modeling should be modeling of the crops. Now, by this time, you can understand that if we place panel top, there are some parts of the ground which has more sunlight, some have shade, and of course, it moves through the day. So you need to figure out the sunlight or the amount of sunlight on the ground throughout the day as the day progresses. So we have the panel output. We also need the light on the crops. Now, our model also calculates the amount of light on the ground. So here's an example. This is a light pattern in Dhaka, Bangladesh for June 22nd. These are south-facing panels, and these are east and west facing. And you can see how the shadow moves. I'll come to this later and explain why this is important. Now, the second part is modeling crops. As I've mentioned before, I'm an electrical engineer. Don't know too much modeling of crops, but what we do is we use the simulator AppSim, the agricultural production system simulator. This is an predict output for example, rice, corn, wheat, and so on. We focus on rice. So this simulator can give you the time series growth of crops. And with time, of course, the crop grows and eventually gives you, let's say, rice. Now, this model gives you the time series output. And of course, from our model, we do know the spatial distribution of sunlight. So once we combine all these effects together, our model and AppSim together, we can predict the output of rice under the panels. Now, one thing I should mention is that the rice or paddy yield is actually dependent on radiation or the sunlight, and this is non-linear. Typical range of sunlight, for example, in Bangladesh is from 15 to 20 megajoules per meter square per day. And of course, if you have shading, the amount of sunlight will go down and your production will go down as well. And this means you need to do rice calculations for each point on the ground. So a lot of calculations there. And then, of course, paddy yield also depends on the temperature. So the local temperature should also be considered. Now, I've discussed about our PV model and energy production. I've also discussed how we couple it with a crop model and figure out what's the rice production. But for economic analysis, we also need to figure out or consider the installation cost, insurance, interest, and maintenance cost of such a system. For example, because we are considering bifacial panels, bifacial panels are typically have a 10% higher price, but the energy production is also higher. And of course, because these are agrivoltaic systems, you need to run your machineries below the panels. So the panel heights are much higher than the conventional PV systems. So the costs are also higher. So we assume about 60% higher installation costs. And we also need to consider the conventional farming costs as well, you know, like for rice production. So all of these give you the initial cost. And once you combine all this, you'll find the profit from the PV system, profit from the rice production, and of course, the net profit. So that's the goal. We need to understand whether this profit is enough or not. So here are some of our results. We did our analysis for 6 locations throughout the globe. We look into rice producing nations such as China, Vietnam, Bangladesh, India, Egypt, and Brazil. Of course, you can see from this insolation map that there are variations in sunlight as well. For example, in Egypt, we have very strong sunlight. Then we also have lower sunlight, for example, in China and Bangladesh. And Brazil is, of course, in the southern hemisphere, so the analysis is slightly different there as well. So if you try to focus here on the blue lines are the monthly sunlight or insolation. You can see that the amount of sunlight is different for the 6 different locations. In Egypt, it's the highest. And then we also have 2 other lines to give you the temperature. Remember that rice production depends on the temperature. PV energy production also depends on temperature. So we need to consider both the insolation and the temperature to be location specific. And also you see in each cases, I have these shaded regions. For example, in Dhaka or in Bangladesh, this is the rice cropping time. So you cannot do rice production any time of the year. So for each country, this is also different. So this is our starting point. We need to consider the local conditions. So based on that, the PV farm output are given here. For example, Vietnam and Egypt have high energy production because of their higher sunlight. And then, of course, remember that Egypt has the highest amount of sunlight, and consequently, rice production is the highest there as well. Here, the bar plots are our simulated results from AppSim, and the marker here shown are the statistical and historical rice production. So mostly it's okay. The simulation results or the predictions are okay. For example, in Dhaka and in Vietnam, the predictions are slightly higher, but I think at the end the trends would be fine. Now, going back to this light pattern on the ground, if you focus on the south-facing panels, you can see that the shadows are mostly close to the panels. The shadow doesn't really move too much for the south-facing panels. But for the other facing panel, you see that the shadow continuously moves from one side to the other, which means if the shadow is moving continuously, on an average, you have a smoother distribution of sunlight. So that's good for the crops. If you have continuous shadowing, then you'll have regions where you have less crops. So typically, you wouldn't want south-facing or north-facing panels for agrivoltaics. You'll want to do the second system. So for our analysis, we'll show results for north or south-facing panels, also the horizontal panels, which are for the east and west facing or east and west moving shadows. We also have vertical panels, which also have lower shadows. So let's focus on the results from Vietnam. So on the x-axis, that's the spacing between the panels. And on the y-axis, that's the energy ratio. So this is the amount of energy you get from the system compared to the optimal or conventional PV system. So when you space out the panels, so as you move along the x-axis, of course, the energy production will go down because you are placing the panels far apart. And of course, if you look into the crop ratio, as you space out the panels, the crop ratio goes up because now as you space out the panels, the amount of shadow is also going down. And of course, for these 3 systems, you can see that the crop production are not exactly the same. For example, if you have vertical panels, you expect very low shadowing, and you can see that the amount of crop production goes up very quickly as you space out the panels. And for south-facing panels, crop production is the worst. As I've explained before, you have constant shadowing there. Now, what should be the performance metric based on these results? One of the performance metric used a lot of times is land equivalent ratio, which is essentially the performance in terms of energy plus performance, the energy of crop. So energy ratio plus the crop ratio. But the problem with this definition is that the economic weight of energy and the economic weight of, let's say, rice, these are not equal. So we really should not be adding up these two factors. But what we should be doing is we should do the full economic analysis and calculate the revenue or the profit. Now, for example, let's say we would allow only 10% loss in our crop. So instead of your 100% crop, you go down 10%. And in that case, for horizontal case, you can figure out what should be your choice of panel spacing. Once you have decided that, you can calculate the amount of energy for that spacing from the first curve, for example, here. And you can see that the amount of energy, it's not 100%, right? This is about like 0.3, which means that the energy production is less than a conventional PV farm, but you know, the land is free, so economically this might still be viable. If we calculate the profit for this case, for an open system, if you just do rice production, your profit per meter square of land area is about 8 cents per meter square. This is just from rice production, no panels at all. And if you design it in this way, as I've explained here, with 10% loss, your profit, which is the summation of profit from the PV system and profit from the crops, the total profit is $237. So you can see that there is about, I don't know, factor of 20, 25 here in terms of profit gain. Of course, your initial cost is higher, but if you can invest, the profit from this land could be much higher. Of course, we repeated this for other configurations. Typically, we see that the horizontal configuration gives the highest economic gain. We repeated these calculations for all the 6 locations I've mentioned before. The trends are similar. For example, in terms of energy, you can see that as you space out the panels, the energy output goes down. And of course, if you space out the panels, the crop production goes up. So there's always a competition between these two things. And if I summarize all the profit, if you focus on the brighter values, these are the amount of profit from the agro PV system with horizontal panels. And the columns on the right, these are profit from just rice production. We used all the economic parameters specific to the locations. So the comparisons are slightly difficult. But for example, if you compare the values in Egypt compared to just producing rice, if you go to APV systems, your profit is about 80 times higher. But what we saw in Brazil is that the gain is not that much high. Our guess is that electricity cost that we assumed was not entirely up to date. So maybe the profit margin might have been slightly higher with a higher tariff rate. But probably we need an updated value for Brazil here. But for in all other locations, the gain in profit is from 20 to about 80% or 80 times higher. Now, these are predictions, of course, but if we want to implement these systems, there are other challenges. So let's focus first on the implications. What would happen if we want to expand APV in a national scale for any country? So first of all, what we think is that it will give a sustainable growth in energy. For example, in Bangladesh, 1/3 of the whole country is rice fields. So a lot of places to place panels. And if we do place the panels, what we predict is that by just 20% expansion of agrivoltaic systems, we can produce 6 times more electricity compared to what we have now. So maybe we can make a plan for 50 years easily. Of course, this will create more jobs, and then because we're providing extra infrastructure in croplands, so we can do more advanced monitoring, and that might help with crop production as well. So in terms of challenges, first is, of course, technological challenges, because we need to redo our civil and architectural designs, the wiring, layout, safety, grid connections from the croplands. These are the things we need to think about if we want to move forward. And then, of course, there has to be relevant government policies, how much crop you would allow to be lost. And for example, in Bangladesh, there are a lot of small landowners, and the lands are adjacent. So they also have to agree, they all have to agree on sharing the land for APV systems, which is very difficult. I mean, trying to make a lot of people agree on one thing. And of course, the business model. So what percentage of the profit should the investors get? What percentage of the profit should the landowners get? What profit does the farmers get from APV systems? For example, if you lease money from landowners, would the farmers be willing to do rice cultivation at all, because they're getting extra money just by leasing out the lands? So these are some issues in terms of business model and policies which need more thought. A roadmap for expansion would, of course, be different for different countries, but it might be similar. So here is what I think might be a roadmap for Bangladesh. Bangladesh, of course, is a agricultural country. Of course, I've mentioned 1/3 of the country is rice fields. We have a lot of research in agriculture. And now we also have a lot of work in PV and expansion in PV as well. But we haven't really combined these two systems. So there has to be a lot more research on this. Of course, we don't use too many bifacials yet, but that could be another option. We need trainings, collaborations, predictive models, and then curriculums to teach the upcoming students. Of course, there has to be some policy making, and then a master plan for investment in a national scale. And all of these things has to be tied together in terms of energy, food, clean water, economy, and job creation. So at the end, it does seem like economically APV is very lucrative, but yeah, I think the challenge is in terms of implementation and policy making. That's one of the larger challenges. So finally, I'll end there, but I would like to thank the project team, Shajib Ahmed, who was the RA in the project. He did all the calculations here. And our collaborators, Professor Anisul Haq, Professor Muhammad Rizwan Khan, Professor Ashraful Alam from Purdue. This work was funded by UIU IAR, and also computational support was provided by UIU IAR and BDREN. And of course, for all my works, I always need to thank all my students to maintain the research. So finally, thank you all for patiently going through the talk. If you have any questions, I'll try my best to answer. Thank you.
Yeah, also thank you very much from my side. I think that was a very interesting presentation into your work. So as I already said, if you have any questions, you can either raise your hand and ask them verbally or type them in the chat. I think there's already one question from Simon La, which is, what distance from the module to the ground have you considered for the vertical system? And what vertical module height did you consider, 1 or 2 modules in height? You can also read it in the chat if you like.
Yeah, I got it. So maybe I can go back and find one of, yeah. So as far as I remember, for compared to the module size, I think the height was about 3 to 4 times compared to panel size. So for vertical systems, we did 2 analyses. One is with the 3 times height, and the other with a lower height. The one with the star, that's with a lower height. And of course, you can see that this has slightly higher profit between the 2 vertical systems. That's because when you have the lower height, and of course, for vertical systems, the costs are also lower. I think these costs were taken from an NREL report. So that's why the profit is higher. So yeah, I think that's what the question was, right, in terms of height?
Yes. Did you also answer the second question with the vertical module height?
Yeah. So as I mentioned, the vertical heights, we have 2 options, one with the higher height, the other with the lower.
Okay, then there is another question from Sekbiji. I hope I pronounced it correctly. Sekbiji. You can ask your question.
Yeah, I don't see it in the chat.
No, he raised, or she raised the hand. Maybe then another person raised the hand. Özal, maybe you want to go then.
Yes, can you hear me?
Yeah.
Try to share my camera. Hi, Ryan. Thank you very much for a clear presentation and this great presentation. What I was wondering that you focus on the profits that would increase by the help of the agrivoltaic system, but when we look at the amortization period, payback time, did you also make calculations about it for each location?
Yeah, we didn't look into the payback time. So I think for the bank loans, the period was about 10 years. I don't exactly remember. We should have mentioned it in the paper or in the supporting document, but I think it was about 10 years, although the lifetime was about 25 years.
Mhm.
So for the payback, yeah, we didn't do any calculations on the payback period. So
Okay.
for the profit, what we do is the LCOE. We do the LCOE and find the difference between the tariff rate and the LCOE.
Okay, thank you.
Okay.
Okay, I think now Sekbeji has managed to open his microphone.
Yes, thank you. Thanks to the presenter for this wonderful work. I hope I'm audible enough that you are able to hear my voice.
Yes.
Yeah, yeah.
Okay, thank you. So my first question is actually to find out if the model you use is compatible with other crop model like sticks, because your case was rice, another model was used. So if the model you use in terms of metrics, in terms of the PV, the electricity model you use, electricity production model you use, is that compatible with other crop model for someone, for instance, who wants to experiment or run some simulation with maybe horticulture production, which is not typically those crop production?
Right.
Yeah, that is the first question. Then the second one is to know also if uh, your model is available. Is it free available? How do you get access to it if someone wants to experiment the model in another part of the world? I'm just saying that I'm currently working on agrivoltaic as a PhD student, and I find what you actually did wonderful. So I'm thinking of how this can be maybe learn from what you have done so far and see how to adjust it based on the context of West Africa.
Okay. Yeah, for the first question, yeah, I think this model can be integrated with other crop models as well, because these are two separate models, right? For our PV model, we have or we calculate the light distribution on the ground, and that light distribution is then fed into a crop model. So for each point on the ground, you'll do a crop production analysis. So in that sense, yes, you can couple it. We used AppSim. Someone else might use some other simulator as well. And for the second question, currently this code is not open for all. We have been working on the documentation for last few months, but we are planning to make it available for others as well. But it will probably take some time for all the documentation and cleaning up the code. But yeah, that's the plan, and hopefully maybe in 6-7 months these things would be available for others as well.
Yeah, okay. Just to going forward, going forward, I wanted to know, was that written in Python, R, or if can people get connected to you to know more about it, and which time collaboration can be done through a kind of working? Because more than the modeling, I'm doing also experimentation. So
Okay.
it's to be good to say, okay, modeling this is what is given. Then in a kind of practical terms, this is what can be done. So to
Yeah.
not get maybe bother other people in the panel, if I don't know if I can connect it to you, maybe via ResearchGate, then we pursue the discussion.
Yeah, sure. Yeah, you can always email me, and of course, I think if you want to
Okay.
write down my email address, but Yeah, currently we know how to do modeling for rice. We haven't done anything else. But yeah, if you have experimental results and want to collaborate so that we want to, if you want us to do simulations, yeah, I think that'd be a good idea. And the code, this was written in MATLAB. So
Okay.
yeah, not in Python.
Thank you.
Okay.
Yeah.
Okay, so I go to the next question because there are still some left. So from Jeremy Davis, it's about, the question is, what about options for retrofitting existing utility scale solar installations? Maybe not an option given the probable panel heights.
Yeah. Yeah. So, for example, at the beginning of the talk, I mentioned two different options. One is that you start off with a cropland and place panels on top. So these, what you would do is for on top of major crops like rice, wheat, and all these things. The other option is that if you want to do shade tolerant crops like vegetables, then below the conventional PV systems where you have a lot of shade, you might be able to do the shade tolerant plants. But yeah, I don't have any quantitative answer on that. I've seen people trying it out, but yeah, we haven't looked into that in details, but that is also an option.
Okay, so I think that answered that question very well. Thank you. Then we can go to Ulf Tollaksen, and he asked what was the share between the PV and rice profit, respectively. And he also asked whether there's a full report available already.
Yes. Yeah, we have a paper on this. If you want, you can email me. I can email back the papers, or if you want to share it through the lecture series webpage, you can do that as well. It's in Applied Energy. I think if you want to write it down somewhere here. Yeah, so this is the paper in Applied Energy. If you want, you can email me and I can share you file. And in terms of yeah, the shared amount of profit. So profit from, for example, in Vietnam, profit from rice would be about 8 cents per meter square of land. If you might lose about 10% of the crop, so it will not change by much. Maybe it will become 79 cents or 7.9 cents compared to 8 cents. And the total profit is 2.37. So it's like $2.29 per meter square. That's from PV. Does that kind of answer the question?
I think so.
Okay.
Maybe I just have a quick follow-up question. Why do you think that, or I can kind of see that there's a tendency that the horizontal PV is the most profitable?
Yeah.
Can you explain why that is so?
Okay. I think one is that because you're spacing out the panels too much. So because these are bifacial panels, you can get sunlight from the back as well. So as you space out the panels, you have more chance of collecting the reflected light. So you want to both face the ground and face the sky as well at the same time. So I think in that sense, that kind of gives you the maximum energy. And because the electricity price is higher than rice, so you to get as much as electricity possible.
Yeah, that makes sense. Okay, I think also Norman Hanifa raised the hand, so maybe you can. Yes.
Hi, Ryan. Thank you very much for the great presentation, and it was really nice. I enjoyed a lot. So what I understood with this horizontal and the vertical is that with the vertical, so can we generalize it that for the vertical uh, alignment, it's suitable for the vegetables because those are shade tolerant. Is that correct?
Um, well, for vertical systems, you typically would have less shading.
Mhm.
So you need a lot of light, then I would go for vertical ones. If you have densely packed panels, for example, also if you have like south-facing panels, then you go for the shade tolerance one, shade tolerant plants.
Okay. And one more question regarding that, like for example, the PV could be like one of the a supporting technology to a decentralized system, especially in the rural areas and in the sub-Saharan region. But what I believe that when it implemented on a commercial scale, will it be a conflict in the demand? For example, most of the time, there's no, and oftentimes when for the project there's no demand of equivalent of that. So do you think that it's a conflict?
You mean demand of energy?
Yeah, exactly. Yeah, I meant
Yeah,
demand.
of course, that's a problem for any PV system, right? So in that case, you would have to expand accordingly with storage systems or batteries. So that's a problem for any PV system. So
Mhm.
I think in that case, the solution would be similar to what you would do for a PV system. So
Okay.
for now, I would guess, yeah, either you would have to use batteries, or during the daytime you would use the energy from the panel. During the night, you might use some other peaking power plants
Mhm.
for extra energy production. But
Okay.
yeah, I think there might be other options. I don't really specialize
Okay. Okay.
in that area.
Okay. Okay. Thank you so much. Thanks a lot.
Okay, all right.
Okay, so I think now we just ask the last questions because the time is coming to an end. So if you have any further questions, I think it's better to email it, maybe directly to Dr. Ryan Khan. So now we come to the last questions. One is whether soiling will accumulate on the PV panels and whether you calculate the soiling loss for calculating the profit. Yes, and
Yeah,
I think there's also a general question whether you will work on that issue.
yeah. Typically, closer to the farmlands, we expect less soiling, but less doesn't really mean zero. So that is an issue. But yeah, if the soiling is low enough, we may not need cleaning, because in such areas you would of course expect rainfall as well. But yeah, this is also something to think about. We haven't thought about analyzing this yet. But yeah, this is an interesting aspect of it as well.
Okay. Then we have another question, which is regarding the temperature input for the crop model. And the question is whether you calculate with another temperature under the panels than at the open field.
Yeah, I think we took a shortcut there. Yeah, we didn't use different temperatures. We used the same ambient temperature for the crops and for the whole system. Maybe not entirely correct, but maybe for the prediction, it would be close enough.
Okay. And there's another question which follows up, which is regarding the albedo and which albedo you considered.
Yeah, typically for rice, albedo ranges between 0.15 to 0.3. We took an average and used the average value.
So the average value for rice.
Yeah, so like average of 1.5, 0.15 and 0.3, so 0.2 something.
Mm-hmm. Okay, so the last two questions. So these are, how do you determine the rice cultivars in the APSIM model, and is the same rice cultivar applied in all countries?
Yeah, for rice, we use the same APSIM system. We changed the temperature, we changed the I think, of course, the sunlight. We also changed the soil model for the different locations. That kind of plays an important role as well. And also the watering system was assumed automatic. So whenever it needed watering, we assumed that the watering was done. For rest of the things, it was set as default values from APSIM.
Okay, so now we're coming to the last question, which is basically the reasons why you chose the specific countries you did the calculation in.
Yeah, so these countries, first of all, these are rice producing countries, of course, and also they have enough broad of a spectrum in terms of sunlight and temperature. So we wanted to see if the predictions we make are general in terms of gain in profit. So that's why we chose it. It was because of the ambient conditions in terms of sunlight and temperature.
Okay, so I think we can wrap it up now. I think if you have any further questions, yeah, you can maybe write it directly to Dr. Ryyan Khan if that's fine for you. I think there was a question whether you can type in your email address. Yeah, exactly.
Yeah.
Perfect. So I also type in again the link with our program and the link for the own cloud. If you agree to that, we can also upload your presentation there.
Sure.
And for now, I just say thank you very much. I think that was a really interesting input also from the region. And I hope that you will make further research there and can present it again here, and maybe that offers you some networking opportunities too. So yeah, thank you very much. That was a really nice presentation. Next week, we're gonna have a German presentation. But the upcoming week after next week, we're gonna have another English presentation, which is also about the installation cost. So it's kind of in the same field subject-wise. So thank you to you all for being here and to listening and to asking all these questions. I wish you a very nice rest day, and I wish you a very nice evening, Dr. Ryyan Khan. And
Thank you.
yeah, so see you next week, hopefully, or the week after.
Okay. All right. Thank you again. Yeah. Have a good day.
Bye.
Bye.
Thank you. Bye.